Okay, so here we have three interacting tanks, and I am going to show you how to find the height at any given time. And we're gonna do that by first we gotta find out what we're doing with just one tank. So each tank has a cross-sectional area and a height, and cross-sectional area times height, which cross-sectional area being like it's like say these are like cylindrical tanks. It's cross-sectional area is going to be pi r squared for that. And that's irrelevant for right now, but that's what cross-sectional area is. And then we multiply that by the height to get volume. So volume is equal to A times H. And what we want to do is really we want to find the change in volume over time. And to do that, we take a derivative of this. So we get v dv over dt is equal to a dh over dt. And then we can also determine that the rate of change of volume is the rate of change of whatever's going into the tank minus whatever's going out. So we have then dv over dt is equal to q in minus q out. And so therefore we have the area times the height. No. And therefore we have the area times the change in height is equal to Q in minus Q out. And so that's just for one tank. And Q out in this case is equal to some proportionality constant times height to the 1/2. And this height here is not just any height. It's going to be the for multiple tanks. It's going to be the difference in height between the tanks, because if you have one tank with more water in it and another tank with less water in it, they're going to want to equalize regardless of the cross-sectional area. So there's that. So then we can change this Q out into alpha h to the 1/2, or square root of h. And so then we're going to take three connected tanks with each with different cross-sectional areas and different starting heights, and we are going to try and determine the heights with change of time. And so for each of these tanks, between the tanks, we have like a Q. Let's just call this Q, let me draw this a little bit bigger so that way it can be seen even, hang on, if my marker decides it wants to work. So here we have between this tanks 1, 2, and 3, and some levels of height in between each. We have Q1 to 2, and then we have Q2 to 3, and we have the Q out. And then in this case, the Q in is into the second tank. So Q in is into the second tank, and Q1 to 2 is going to be equal to something like alpha times the absolute value of h1 minus h2. And why we want the absolute value is because if we're going to set this equal to, or if we're going to take the square root of this, we don't want a negative sign under the radical. Because if you have that, then you're going to get like complex numbers, and this isn't, that's not something you're going to, and we just don't like complex numbers. But since if this is negative, we still want it to remain negative, so there is something called a sine function, which is going to be like just sine of h1 minus h2. And so that way it is covered for in case like these flip-flop in between like H1 and H2 being less or more than one or the other. So that way we have the sign correct. And then Q2 to 3 is equal to the same thing except for it's going to be the proportionality constant times H2 minus H3 to the 1/2, and that's the absolute value of that times the sign of H2 minus H3. And we keep that the same. And then Q out we already know is going to be alpha times, I guess, just h to the 1/2. And I know I say these are, so yeah. And then what we want to do is determine the change in height over the change in time. So we have area times dh over dt. Well, you can keep it like that from when we do the Python function, but for this purpose, we want it to just be dh over dt. And this is going to be the height of 1. This is going to be the change in height in tank 1. So it's still going to be it's going to be cross-sectional area times in minus out. And no, actually no, it's going to be in minus out over the cross-sectional area. So in minus out for this, so tank 1 right here, the only thing in tank 1 we have is what's going out, and that's Q1 to 2. So that's going to be negative because we don't have anything going into that tank, Q1, 2. And for DH2 DT is going to be also over A, but in this case we do have something going in, so it's going to be Q in minus Q minus Q2 3, and also another thing going in is Q1 to 2, so we're going to add Q1 to 2. And then we have Q out, no, and then we have DH3 dt, the third height, is going to be equal to Q2 to 3 because that's going in minus Q out. So there are all the equations there. And then what we want to do is say we want to have a set point for the height of tank 3, so H3 set. We want to control that with some proportionality constant of whatever is going in. So we want to control what's going in. And to control what's going in, we're going to need something called Kc. And Q in is equal to Kc times the set point height, in this case H3s, minus the actual height. So that's what the rate in is. And then what this Kc here does, there, let me, I guess, just stop for a moment and let you guys see what the board even says, because I know it's a little far away and this camera sucks. But this is an alpha, I promise you. Still an alpha. What this QN does is if you have it like set really low, what you're going to do is you're going to see the height is, so you have your set point here. It's going to start, you're going to see your height go like this if Kc is low. If your Kc is low, it's going to go something like this, and it's never going to truly reach the set point. And then if you have your Kc too high, it's going to look something like this. It's going to be like a damped dampening sine wave, and it'll eventually even out, but it's going to be really turbulent. And that's not usually, or it depends on the situation, but that I wouldn't think that would be ideal. But if you want your KC to be just right, it's going to be something more like this. This is not the best drawing, but you have your set point, and KC equals desired. And so if you have your desired, let me just take this off. And so if you have your desired set point, it's going to go above your set point height, but it's eventually going to even out, and it's not going to have all that turbulent sinusoidal wave stuff that the high controller constant has. And if you wanted to minimize this and actually, or to make it more accurate, you're not going to want to use a proportional set point. It's the worst set point there is. There's like integral set points that are at least a little bit better, and I'm gonna guess some other stuff that I haven't learned yet, which I will probably be discussing in other videos. So for now, that's it for this video.